nothing here. And just be careful what you say about me when I walk out the room, in other words. Look back at my video. Were you interviewing Tyler? Crane? Okay.
Doesn't look like a government type, right? One of my friends, the IT guy,
yeah, there's diversity effort, right? So I think it matters what your hairstyle is like, or yeah, then they still have rules. Is that right? Yeah, they wouldn't be able to recruit anyone now. Well, show visible tattoos or any tattoo, visible tattoos. Right.
I didn't drink a lot more.
Never got the tattoos. But they're kind of, yeah, probably one followed after the other, right? You drink a lot and then get tattooed.
There's nothing that comes to mind that I want to put like permanently on my body. But I associate that with
In here? Oh, okay, yeah. Actually, I think I'm going to move that test to Monday because somehow I got a day off schedule. There's one more topic I want to cover on Wednesday, finish up this chapter, but yeah. Is that better? Got 2 more days not to study instead of, yeah. Yeah, the 354 test is definitely today. That's sounds like a good way to do it. Yeah, not in, well, you hope not in engineering courses. We're supposed to be, testing more about how well you can solve problems. Of course, a lot of that is having solved problems before, having done the homework. Yeah. Yeah, a lot of biology, anatomy classes are just memorization. So we've had a few students do that. Actually, had a few actually come out of undergraduate electrical and go on to med school, and have had a few go into law school, go into patent law, which I guess there used to be a big demand for that. I don't know. I don't think like there's much of a demand for lawyers at all now. That really. Oh yeah, I think it really helps if you want to look at going into med school, have an engineering undergraduate. Yeah. We yeah, which they could be back today or could be what next week sometime. Um, so this week and next week are advising, so you should start registration. I guess for seniors, when do you actually register? Is it in 2 weeks then? Okay, November. It starts on Monday. Okay, so you guys should all make sure that you meet with your advisor this week so that you get pre-approved for, especially your gen eds. I mean, you're not going to get locked out of any of your required classes, but if you want to get into a particular gen ed, that's the advantage of being a senior. is you get to register first. So you should get your choice. Okay. So moving the exam here, it's on the syllabus as the exam is scheduled for Friday, but I'm going to move that to Monday. I want one more day of lecturing. I want to talk about time division multiplexing on Wednesday. So we'll review on Friday then for our next exam on Monday. But today I want to talk about actually differential pulse code modulation, or it's DPCM. And I guess we were just saying, well, there's not much memorization in engineering, but there's a lot of acronyms. So all these pulse code modulation, delta modulation. Differential PCM is kind of a hybrid between pulse code modulation and delta modulation. Okay, so I'll say here it's similar to delta modulation, or DM, but uses an L level quantizer with levels plus or minus delta, plus or minus 3 delta, plus or minus L minus 1 delta, which is the same as actually pulse code modulation, right? And then here L again would typically be a power of 2 instead of just 2 levels. Okay. So you could also say it's similar to pulse code modulation, but there's feedback involved. So the feedback is an attempt to try to reduce the required sampling frequency. So delta modulation has this high sampling frequency required, much greater than the Nyquist rate, but a low binary bit rate. The bit rate is equal to the sampling rate. In pulse code modulation, you sample at the Nyquist rate, but the bit rate then is n bits times the sampling rate. So I'm not really going to discuss this in any detail other than to show you the block diagrams so that you get an idea of what's going on with this. It's not a popular method. Again, for the reason is we've gotten into storing so much of our information on a computer. It's already been pulse code modulated, with audio or video. It's already in a PCM format. So most of our communication systems are actually designed to transfer bits, pulse code modulated systems. So a lot of these analog to digital conversion methods, the modern ones all focus on actually PCM. So these others aren't used as much as now as they were at one time before digital storage became common. So with delta modulation, we still had this feedback system, but it was just a one sample delay. Now in the feedback loop, instead of a one sample delay, we have a filter that may use multiple previous samples. Okay. And then that's fed back and subtracted here. It's called a prediction filter because the idea is we're trying to predict what the next sample would be based on previous samples. And then the last. So the idea we would quantize using fewer levels. Instead of an 8-bit quantizer here, we could use the differential pulse code modulation and quantize using 4 bits because there's redundant information. The feedback system would allow that and still allow us to get the same level of accuracy. So you can imagine analysis of this is, theoretical analysis is difficult. So you have to use, you could resort to computer simulation to actually measure the error. And it's going to depend a lot on the type of input signal. If there's a lot of, if your samples are highly correlated, this can be pretty effective. So this is a differential pulse code modulation transmitter. But DPCM uses a, it's called a prediction filter, but you can think of it just as a regular digital filter. Instead of just a simple TS delay, which is what we used in delta modulation. So M hat of NTS would be here, I equal 1 to P of WI MQ of NTS minus ITS. So it's a pth order digital filter. And there's a whole theory related to actually calculating the filter weights, the WI. They're computed to minimize the error between MNTS and M hat NTS. Okay. There are n equal log 2 of L bits per sample. So the binary output rate is RB equal NFS. But the idea here is that hopefully FS will be less than that required by a delta modulator, where the binary rate is just FS. Okay. But we could use fewer bits than would be required in pulse code modulation. So there's a sweet spot there for the, we'd like to minimize the binary rate. So again, it's kind of a hybrid. You could say it has the best of both. You could also say in some sense that it has the worst of both systems. The big advantage of delta modulation is the simplicity of the system. You don't have to have any sort of encoder. It's just 1-bit output. It's essentially a comparator. So it's a really simple system. Well, you've lost that simplicity now. So this is actually even more complex than a pulse code modulation because of the feedback loop involved. So it is a compromise or a hybrid system. The receiver you have the decoder that would look at the code words and produce, again, the quantized output levels. And then we feed that back to regenerate. Here's our quantized message that comes back into, it's the same prediction filter that we use at the transmitter. And then we just have to low pass filter to recover our approximation to the original message. So this is a differential pulse code modulation receiver. Okay. But what I want to talk about now is a completely different topic. And it's one maybe you've not given much thought to. But it's called line coding, or how to actually select the voltage waveform that would correspond to your binary bits. Okay. And the advantage, and there's a number of different ways to do that, some of which are illustrated on this in this figure. Okay. But you know, the simplest way might be, you know, well, do I use just a single power supply that I switch between 0 and 5 volts, 0 for a 0 and 5 volts for a 1? Or, you know, maybe I use plus or minus 5 volt supplies. Is there advantage to doing that over using a single supply? Well, obviously, if I switch between plus and minus 5 volts, I need 2 supplies, so there's an extra expense there. But is there an advantage to doing that? And then there are other differences in these line codes as well. They have a number of different advantages and disadvantages that we want to think about. So that's what we'll be talking about the rest of the lecture today, is some of the different ways you can use to convert ones and zeros into voltages, and what are the advantages and disadvantages of these different techniques. So these are called line codes. Okay. So this is a figure from the textbook, 520, and I'll talk about each of these. Not all of these different codes are indicated here, and there's different classifications. So you can have unipolar return to 0, bipolar non-return to 0, polar non-return to 0. But the simplest is what you're familiar with. I think that what's called a unipolar or on-off code. And these are in figures A, C, and F. So you may want to reference here in your notes. This is figure 520 from the textbook. So the advantage of these is that they require only a single supply, a single voltage supply. So they're less expensive. But they have a DC bias or average value. You know, if this is going from 0 to 5 volts, then this has an average value of, you know, 2.5 volts if you're transmitting as many zeros as ones. So that makes it difficult to pass through a transformer if you're using transformer coupling. It also is wasting power. Okay. Turns out that this actually uses more power than switching between plus and minus 2.5 volts. Okay. It also turns out, the other thing that we'll see is that these different line codes actually have different bit error rates. Okay. A line code that switches between 0 and 5 volts actually has a greater error rate than a line code that switches between plus or minus 2.5 volts. Okay. So DC bias that wastes power. Now, with regard to two power supplies, there's two terms that's used. There are polar codes and bipolar codes, and we'll talk about both. But examples of polar codes are, for example, B here, which is switching between a negative voltage and a positive voltage. Let's see, D is another one, as is E here. So that you have to have two supply voltages. So that would be a disadvantage. Require two supplies. But have a lower bit error rate. There's another acronym for you. It's called BER. And we'll be seeing more of that over the next couple weeks for the same transmitted power. So this may be, although there's extra expense in getting this second supply, if it reduces the error rate, or you get a reduced error rate for the same transmitted power, or the same error rate for less power, it may be a good trade-off. Okay. Another classification is you can have what are called return to zero and non-return to zero. And these have acronyms associated with them: non-return to zero, codes, and these are A, B, D, and F. And they have a constant level over the entire bit interval, TB. So the non-return to zero, a zero pulse is if the bit interval is capital T underscore B, a non-return to zero pulse has a constant level for that entire bit interval. So it's 0 for TB seconds, it's 1 for TB seconds. If you have consecutive ones, it's a constant level. If you have consecutive zeros, it's a constant level. So you see that here. Even this is a unipolar non-return to zero. This is a polar return to zero. Now, unlike C, where we'll talk about here, the pulses are less than the entire bit interval. Okay. So C is an example of a return to zero pulse. This is actually an NRZ. This is a return to zero. And as long as what you see in the bit interval is actually less than, isn't constant over the entire interval, it's a return to zero. Okay, so why would you ever use a return to zero? Well, the non-return to zero have the smallest bandwidth. And you want to remember this approximation as we start dealing with different pulse waveforms. That we know the Fourier transform of a pulse is a sinc function. The width of that sinc function is approximately equal to, out to the first null, it's 1 over the pulse duration. Okay. So we say that the required bandwidth is actually a function of the pulse width. So the wider the pulse, the smaller the required bandwidth. Okay. So that's an advantage for these non-return to zero pulses. They have the widest possible width, so they would resort in the smallest required bandwidth. So what's the disadvantage? but they can present clock sync problems at the receiver. Okay, so one of the things we have to do at the receiver, we've talked a little bit about this, but not in any detail, is that we're getting this waveform plus additive noise. So at the receiver, we need to sample the waveform and then we compare it to a threshold. Okay. Well, we need to sample it at a particular time. Ideally, we would like to perhaps sample it right in the middle of the bit interval. Think about this one pulse here. We want to sample it right in the center of that bit interval. Okay. Well, in order to do that, we have to have a clock at the receiver. Okay. Now, a couple different ways you can do that. We can transmit the clock signal with the data signal. That's done in some transmission protocols, but that's twice as much copper wire, right? So there's expense associated with that. The other technique, and it's kind of like pulling out, using a phase lock loop to pull a sine wave out of a transmitted signal. It's actually using the signal characteristics itself to pull out a clock signal from the data signal. Okay. And that's possible with some of these techniques. Okay. That because of the oscillation here, you can think of this as maybe being a periodic waveform that has a fundamental frequency that's equal to the clock frequency, and we can pull that out. Now, the problem with the non-return to zero signals, if we've got a constant string of ones, we've got no transmissions, or a constant string of zeros, we've got no transitions, from no changes in a pulse. So it makes it difficult to derive a clock signal from a non-return to zero. If you've got, again, a long string of ones or a long string of zeros, you can lose clock synchronization if you're using one of those techniques that derives a clock signal from the data signal. Okay. There are some simple techniques that are used to solve that problem. One is to actually scramble the data before you transmit it to try and ensure that you don't get a long string of zeros or ones. Then you have to descramble it at the receiver. Another solution to that is to actually use what are called return to zero, or RZ codes. And C is an example of that here using the shorter pulses. We'll see that D and E also have transitions that can help with driving a clock. But the return to zero codes have non-zero levels only over a portion of TB. So let me continue this description here. These have a larger bandwidth, okay, because they're using smaller duration pulses. So that requires a larger transmission bandwidth, but easier clock synchronization, and also less power. Okay. Because again, the pulse is not at a constant level for the whole bit interval. Okay. So in figure 520, what we have so far, we could classify A as unipolar NRZ, non-return to zero. B is a polar non-return to zero. Now, how would you classify C? Polar or unipolar? Unipolar or polar? Unipolar, right? And only it's switching between a voltage level and ground. With polar, you're switching between a plus and negative voltage level. Okay. So this is polar. It is a non-return to zero, though. So the one pulse doesn't take up the entire bit interval. It's, in this case, they show it only taking up half the bit interval. But we transmit a one, it's a short pulse, then we return to zero. Here's another one, transmit a short pulse that doesn't take up the entire bit interval like it does here, but it's actually just, in this case, again, as it's shown, it's like half as wide. Return to zero. Here's another one, 0, 0, 1. So you can, decode this 0, 1, 1, 0, 1, 0, 0, 1, right, to match that waveform. It's the same as the waveform in A, but using shorter pulses. It's using a return to zero code. Okay, so this is, C is unipolar return to zero. They don't have, it doesn't have pictured polar return to zero, but you could imagine what that looks like. Okay, so what's going on with the last three? The last three codes do not use the standard 1 high, 0 low encoding. Okay. So D is an example of a bipolar code. And if you'll notice, what makes D unique from all the others is it actually has 3 levels. It's got a ground level, a high voltage, and a low voltage. So it has 2 supplies. A bipolar code uses 3 levels. No pulse for a 0. And then alternate plus or minus levels for 1s. Okay, so you can kind of see what's going on here. There's a 0, so no pulse. This first one we transmit a positive pulse. The next one we transmit a negative pulse. The next one that comes along, we transmit a positive pulse and then a negative pulse. Okay. You might have to think a while about what could be the possible advantage of using a pulse encoding like this. And it is, well, if you invert this, it could still be decoded properly. So again, every time there's a pulse, that's a 1, whether it's a plus or minus pulse. So even if this were inverted, so it were 0, negative, positive, you'd still come out with a 0, 1, 1. So the advantage here would be if you're using inverting amplifiers or digital inverters somewhere in your transmission train, but you don't know how many inverters it's gone through, you can still decode this properly. Whereas certainly with the bipolar or the polar, that wouldn't be true. You'd be making a mistake every time. Okay. So a bipolar code can be correctly decoded even if inverted. So at some point, someone has come along and invented a code for whatever problem you might run into, or it certainly seems that way. The next one, E here, is called a Manchester. Sometimes called a split phase, or sometimes even a twinned binary. You'll hear all of these used. So the code, so this is E in the figure, uses high, a low pulse for a 1 and a low high pulse for a 0. Okay, so let's see, that's this one, right? So every time we have a 0, notice the entire bit interval is here, so it goes low, high. Okay. For the 1, which starts here, the 1 goes high, low. Here's another one, high, low. Low, high is a 0. High, low is a 1. Low, high is a 0. Low, high is a 0. High, low is a 1. So once you understand the decoding, it's easy. You know, the entire pulse interval is made up by, again, a low, high, or high, low. Okay. So this has the advantage of having a transition in every bit interval, okay, making it easier to derive, again, a clock signal from the actual data signal. Okay. Is this one clear, what this one does? Low, high is a 0, and high, low is the 1. So the pulse shapes are either, you know, over the TB interval. If it looks like that, it's a 0. It's a low, high. But if it goes high, low, it's a 1. Okay, now obviously you could reverse that. Where was I at? So that's over here. And then, okay, what's going on with the last one? In a differential code, and this is code F, a transition occurs for every 0, and alternately, you could do it for every 1. No transition for 1. Okay. So that's this last one. There's a 0, so we were previously at a high. So, you know, the level for a 0 actually depends on what the previous pulse level was. So it's high, low. We maintain that level for 2 1s. The next 0 comes along, we switch to the other level. We hold that for 1. When a 0 comes along, we switch. The next 0 immediately follows. We switch again and then hold that for a 1. So we'd be able to decode this one properly, even if it's inverted, because we're just looking for the transitions. Every time there's a transition, we know that that's a 0. Again, with a long string of 1s, we're not going to be able to derive a clock signal there, but with a long string of 0s, we would, because there's still a transition. So all of these have different advantages and disadvantages. In addition to choosing a line code, you might also ask, what's the best pulse shape? Okay. Is a rectangular pulse shape actually the best to use? It turns out it's not. It actually depends on the properties of the line. Okay, we'll see that some pulse shapes actually lead to interference between consecutive, can interfere with the next pulse when the pulse gets stretched out. So we'll look at different pulse shapes and what would be an optimum pulse shape to use. That's not until the next chapter. So let's say you've got 1, 0, 1, 1, 0, 1, 0, 0, or so you might want to mark these off. And then, so this is the binary sequence. And then have sketch unipolar non-return to zero, sketch, I didn't leave myself enough room for all of these, so squeeze them in here. Unipolar non-return to zero, polar return to zero. So we'll need some reference level here on these. Bipolar return to zero. And then finally, Manchester. As the last one. So I'll give you a few minutes to actually sketch those codes. I mentioned at the start of class, our next exam here is supposed to be on Friday, but I'm pushing that back to Monday. So I still have one more lecture that I want to finish up this chapter. And then also that this week is pre-registration week for seniors. So you should be meet with your advisor. I think most advisors are meeting via Zoom. So make sure you have the Zoom link that you need to meet with your advisor. This may actually turn out to be a better way to do this, so at least both parties can pull up the schedule then on their computer. So let's look at the first two, and then I'll give you a little bit more time. So I didn't leave myself really enough room here. You kind of need, you want a reference level or a 0 volt level on all of these. But a unipolar non-return to zero would be, a high level for the entire bit interval. Okay. So, and since it's non-return to zero, it stays high. 0, 1, 0. So that would be the unipolar return to zero, non-return to zero. The polar return to zero, so it would be high for a 1, but then return to a 0. And then for a 0, it goes low, but then returns to ground. So the next one's a 1, so it's high, back to 0 volts, high, back to 0 volts, then low, back to 0 volts, high, back to 0 volts. Any questions about those two? Polar return to zero and unipolar non-return to zero. Give you a couple more minutes to work on the bipolar return to zero and the Manchester. Okay, the bipolar return to zero, that's example D here. And then again, you could alternately have pulses on the zeros, but here with the bipolar, there are 3 levels, but there's no pulse on the zeros. So no pulse on the zeros. There's a 0, and then these 2 zeros. And then we alternate on the 1s. So it'd be, and you could start out this either high or low, but it's high, low, alternate high, back to 0. And then this next one would be 1. So that would be the bipolar return to 0. For the Manchester, zeros are low, high. So I find it easiest to first do all those. So find all my zeros, do my low, high pulses. And then the 1s are high, lows. So high, low, high, low. I have to jump back high, low, and then high, low would be the Manchester. Any questions about those? And they've all seen applications in different, and there are certainly, these aren't all of them. But these are some of the more common line codes that are in existence. Never could have imagined that it would be this complicated just to transmit ones and zeros. Okay, that's it for today.